everyone. It feels really incredible to be here. This is my 5th Brighton Ruby, but it's my first time up on stage. You can find me online there, and right now I work as a principal programmer at 37 Signals, but importantly for today, I'm not a mathematician, not yet at least. For now, I'm just a computer scientist with a deep love of mathematics. So I'll start this presentation with a quick heads up, especially if there are any mathematicians present in the room. I'll be explaining some deep concepts intuitively. This means I'll favor intuition and brevity over formal rigor. This is on purpose, not to get lost on complex proofs and not to lose most of the audience after 5 minutes. Okay, so having said that, we shall start these presentations with 4 symbols, P, N, A, and dash. So we can combine these symbols to form expressions. And for example, MPA dash P dash A is an expression. And some of those expressions are going to have specific meanings, and we are going to call those sentences. Okay, so with that, now we are given a printing machine that can print some expressions, but not others. So we are going to call an expression printable if the machine can print it. We assume that if an expression can be printed, it'll be printed eventually. And now we are going to see some propositions using the 4 previous symbols. So for any expression x, P dash x means x is printable. And MP dash x means that x is not printable. So with a quick example, we will see this quickly. So if we have the expression P dash ANN, that means that ANN is printable. And MP dash PPP means that PPP is not printable, okay? So now we are going to define the associate of an expression x as x dash x. And for that, we are going to define the same expressions as before, but just for the associate. So we have PA-x, it means the associate of x printable, and the same thing with MPA. So for the associate of x is not printable. So going back to our examples, here, so if we do the associate of ANN, that means that ANN-ANN, the associate, is printable. And with the previous one, MPA-PPP means that the associate of PPP, that one is not printable, okay? So now we are ready to define a sentence. Remember, expression with meaning. This is going to be just an expression of these 4 forms we just saw before. So those are sentences, where x can be whatever, an expression whatever, any combination of the 4 symbols. So since we are Ruby programmers, we are going to write a quick Ruby program to check whether an expression is a valid sentence and to print their meaning. So first, I just check if the expression contains valid symbols, which I just did like that. And then we are going to parse it and to say if it's a valid sentence. So here I took the chance to use this newish Ruby pattern matching feature, which I really like it. If you are not that familiar with it, let me go quickly about how this works. So this is going to split the expression by the first dash, and then associate assign the part on the left side to OP and the part on the right side to X. So if we see that with an example, if we have that expression and we run this code, this is going to get this in OP, the first part before the dash, and then in X, the part after the first dash. So this is what this code does. And you may be wondering, if the expression chars don't have any dash to split it, so it doesn't match the pattern, in this case, like for example here, and you run the code, you will get a non-matching pattern error. So this is how this works. It's pretty neat. Okay, so now we can, now that we've parsed it, we can check the left side of the expression to see if it corresponds to one of our 4 possible sentences. So I did it just with a simple case statement like this, and also printing their meaning, as we saw before. So now I'm ready to put everything together in a sentence class that we are going to initialize with an expression. And then to get it the meaning, we are going to use the case statement that I showed before, but just adding a little bit to parse it before. And then here we define the expression of P and X as attribute readers, and like here, and then we initialize them on a parse method, like it's just the same that we saw before. And then we can complete the class with two little methods to check if we have already parsed the expression and to check if the symbols are valid. This was the very first, the method I introduced in the beginning. Cool, so now we are ready to check some expressions. So running this code will yield this result where we have an expression with where the dash is used in the expression but it has no meaning, and a couple of examples of expressions that are not sentences because they don't conform to the four forms that we described before. Okay, so enough with that. We are back to our printing machine. So now we can give a precise definition of truth and falsity for the sentences, and they are the intuitive meaning you will expect. So P/x is true if and only if x is printable by the machine. And then Px is true if x is not printable, and so on. The same for the associates. So it's the intuitive meaning. Okay, so for example, giving us a sentence like P-NA, that means that if it's true, the machine cannot print NA. And so PNA is false, okay? And now we are given a crucial rule. Our machine is 100% accurate. It only prints true sentences. It cannot print anything false. And this has direct consequences. If the machine prints P-X, then it must print X. Because if X were not printable, that statement wouldn't be true. And we know that our machine is 100% accurate. And also, if it prints MP-X, then it cannot print P-ish, because that would mean that X is printable and not printable, and that would be a contradiction, so that cannot happen. Cool. Okay, so now we are ready for our little Gödelian riddle. And if there are any mathematicians in the room, they might know why it's Gödelian, and the rest will know soon. So, can you find a true sentence that the machine cannot print? Okay, I'm going to leave this here for later, but you can continue thinking about it later and over lunch. Okay, so I hope your brains are warm now, but not fried, because we are going a bit deeper. Cool, okay, so many of us, at least me, I hope, love mathematics for its certainty, exact, precise, no room for subjective opinions. But is that so? Well, in the late 19th and early 20th centuries, they were a turbulent time for mathematics. There were Peck paradoxes, especially in set theory, that began to shake the confidence overall in the certainty of mathematics. And there was a growing desire among mathematicians to create a perfectly solid, complete formalization of the foundation of mathematics. But what is actually the foundation of mathematics? Because mathematics is actually not a single entity, but it's rather a collection of formal systems or mathematical systems. But what is a formal system? So a formal system is built of, first, a set of basic assumptions called axioms, rules of inference that let us derive new truths from the actions. We call that theorems. And a classic example of a formal system is piano arithmetic that just formalizes the arithmetic of natural numbers. And the actions are intuitive, usually, like, for example, 0 exists, or 0 is not the successor of any numbers with the natural numbers. So for the formal, I say there are many formal systems, but not all of them are interesting. So for a formal system to be interesting, they need certain properties. A key one is being sufficiently expressive. For mathematicians, this means powerful enough to describe the arithmetic of natural numbers. Piano arithmetic is obviously one such system, but there are many others. Another vital property we want our mathematical system to have is consistency. A system is consistent if it's impossible to prove a statement and its opposite. If we could prove both x is true and x is false, then our system could prove anything, like even falsehoods. So all our proofs will be untrustworthy. So, and we will have 2 questions or theorems. So yeah, consistency is very, very important. And ideally, in our system, we want the ability for the system to prove every statement that is actually true within the system. Anything that's true, we want to prove through our actions and theorems. This is known as completeness. Okay, so David Hilbert was a German mathematician and philosopher of mathematics, and one of the main figures in this quest, in the early 20th century, to provide a secure foundation for all mathematics. He had a program, came to be known as the Hilbert's program, that aimed for a secure foundation for all mathematics. And this required a formalization of all the mathematics, a precise language for all mathematical statements with well-defined rules. Then Hilbert also wanted this formulation to be consistent, so a proof, he wanted to have a proof that this formulation will never lead to contradictions. Of course, he wanted his formulation to be complete, ensuring that we could prove every mathematical statement. And crucially for our story, he introduced another requirement, decidability. This means that we could find an algorithm, it's a sort of mechanical procedure to determine the truth or falsity of any mathematical statement. This one, decidability, this idea was particularly ambitious at the time because the very concept of algorithm didn't exist. It wasn't rigorously defined or anything. But that was the dream that mathematicians had at the time, like some sort of universal method, a step-by-step mechanical procedure where you could decide the truth or the probability of any mathematical statement. This grand challenge that was proposed by Hilbert in 1928 became known as the Entscheidungsproblem, which is German for decision problem. So that was Hilbert's dream. Unfortunately, here is where the existential crisis comes. In 1931, a logician, mathematician, and philosopher as well, called Kurt Gödel, published 2 theorems that will show that this mathematical dream was not possible. Gödel's first incompleteness theorem delivered a stunning blow. This theorem states that any consistent formal system powerful enough to express basic arithmetic is necessarily incomplete. So this also implies that if such system were complete, it would have to be inconsistent. So now think back a bit to our printing machine and the riddle, find a true sentence that the machine cannot print. This is actually the heart of it. So if we revisit Hilbert's wish list for mathematics, we can see that we know that an inconsistent system is a disaster because you can prove anything and it will render all your proofs untrustworthy. So consistency is non-negotiable. That means that we must sacrifice completeness because of Gödel's theorem. Okay, and then what about decidability? Well, the Gödel theorem also casts a long shadow on decidability, because if there are true statements that cannot be proved within the system, how could we find a general algorithm to decide the truth of all statements? Right? It seems impossible, but he didn't prove that. But to keep advancing on this, we need to wonder, but what's an algorithm anyway? They have no rigorous definition for this at the point. So, taking Gödel theorems as a starting point, a brilliant British mathematician was formalizing the very idea of what it means to compute something, or what an algorithm is, and what kind of problems can be decided by an algorithm. This mathematician was Alan Turing. You may be familiar with him. It's actually not this one. You may know him from here. Okay. So Alan Turing is considered by many the father of computer science. In 1936, Turing published a paper that reformulated Gödel results, replacing the arithmetic of natural numbers with a new intuitive device that he invented called Turing machine. Many of you may know Turing and many others for his vital code-breaking work in World War II. But this theoretical work arguably had an even more profound, lasting impact. The paper that he published in 1936 has been quoted often as one of the most influential papers in mathematics history. So a Turing machine that he invented, that he introduced in this paper, is a deceptively simple theoretical device. It has an infinitely long tape, thin like a strip of paper, infinite, and a head that moves and reads and writes symbols, and then a set of rules. Yet, this simple machine is powerful enough to perform any computation that any modern computer can. So it beautifully captures the idea or intuitive notion of what a mechanical procedure or algorithm is. So the Turing showed in that paper that any problem solvable by a step-by-step mechanical process, an algorithm, can be solved by a Turing machine, and vice versa. This is the core of what is known as the Church-Turing thesis. The set of problems that theoretical Turing machines can solve is the same set of problems that we can solve with Ruby, JavaScript, or any programming language. So, if Turing's universal computing machine will be capable of performing any conceivable mathematical computation, if we could represent it as an algorithm, are there problems that they cannot solve? And could we use them to answer the question on decidability of mathematics? Well, the answer is yes. So, in his paper, Turing connected the abstract Entscheidungsproblem to a very concrete computational question. This is known as the halting problem, and this problem states, can we determine if an arbitrary Turing machine, given an arbitrary input, will ever halt or will run forever? This is the halting problem. So this applies in the same way to any other model of computation that is equivalent to Turing machines, which also includes the programming language we know, like Ruby. So generalized, the halting problem is the problem of determining whether an arbitrary computer program and an input will finish or continue to run forever. So then in his paper, Turing proved that the halting problem is undecidable. No general algorithm, no Turing machine, can exist that solves this problem for all possible inputs. And because he had, in the paper, he had linked this to the Entscheidungsproblem, this meant that Hilbert's dream of a decidable mathematics was also impossible. So we can look quickly to an intuitive sketch of the halting problem and decidability proof that Turing presented in his paper. He did it using Turing machines, defining a formal mathematical proof. But since we know that Turing machines can solve the same problems that Ruby can, so we are going to sketch the proof using Ruby. So to start with the proof, we are going to assume first that the halting problem is solvable in Ruby. So this means that we will have some gem called halting that provides a module with a method to check that whether a given program and an input halts. So we assume that this is true and exists. To simplify, we are going to assume that the Ruby program is given just as a method, because we always can put everything together in a method in Ruby and just use it as the program. Okay, so if this exists, if this gem exists, we can use it in another Ruby program that we are going to write. And this Ruby program is going to have a method that is called paradox method. So then in this method, so we are going to use our halts method with our new paradox method. So here we are using Ruby's method that returns a method object. So here, so we are passing that to halts, and if this returns true, so if the paradox method halts, we are going to loop forever here. And if not, we are just going to stop and return true. Okay? Cool. So we have the problem, the program, and now we are going to analyze it. So If halts with paradox method as input returns true, it means that paradox method halts. So if this is true, this halts. But we can see that actually it doesn't. It loops forever, right? So we have this. Now, assuming that halts for paradox methods returns false, in this case, we will be in the else. So we will be here, and we see that this program halts and returns true. Okay, so what where we have arrived is that paradox method halts if and only if it doesn't halt. So this is a contradiction. That means that our initial assumption that such gem and such Ruby, like such gem, such solution in Ruby to the halting problem exists is false. Okay, so now let's go back a little to the Church-Turing thesis. Remember, this thesis says that the set of problems that Turing machines can solve is equivalent to the set of problems we can solve with our computers now. It's the same. So you might be wondering, what's that Church there? Well, so Church comes from another mathematician, Alonso Church, and incredibly, at the same time and working independently, Alonso Church also proved at the same time that the Enchidun's problem was unsolvable. And he did so with a different model of computation. He invented this. It wasn't Turing machines. He invented a different model of computation that is called lambda calculus. Some of you may be familiar with Haskell. Haskell programming language is deeply rooted in lambda calculus that he invented just to show the undecidability of mathematics. And lambda calculus and Turing machines are equivalent. The class of problems they can solve is exactly the same. And both systems capture formally our intuitive notion of algorithm or mechanical procedure. And at the time, this was huge. This was basically the birth of computer science as we understand it today. So, Gödel revealed fundamental limits in formal mathematical proof, and Church and Turing revealed fundamental limits in computation. Just as there are true mathematical statements that are unprovable within sufficiently expressive, consistent, axiomatic systems, there are problems that are unsolvable by computers. So what? At this point, you might be thinking, well, but this is a Ruby conference. Where is the Ruby? Here, beyond that tiny cameo in the beginning and that paradox thing that it can't even exist. I want my money back. Sorry, Andy. Well, just as mathematics faced this existential crisis in the early 20th century, we in software development are facing our own little crisis today with the rise of AI, LLMs, and looming predictions of us being made irrelevant by machines. So I wanted to bring you a little perspective and perhaps inspire you a bit in these times. So on one hand, after this small existential crisis, mathematicians went on to publish some of the most influential papers in history, and they laid the foundations of computer science and basically everything we do now. So questioning your own existence sometimes can be used to push you forward. On the other hand, tools like LLMs shouldn't actually diminish the sheer joy and wonder of learning and critical thinking and knowing the fundamentals of your profession, from abstract mathematics and theoretical computer science to, solid-state physics that powers most modern electronics, if that's more your thing. For me, there is unique, pure beauty in the formal constructions of logic and theoretical computer science, because they are free from physical constraints. So you can, for me, I admire the beauty of abstract ideas and formalisms, just like you can admire art or nature. And you can find deep, very deep satisfaction in following and grasping a perfect proof where everything fits. But these topics can feel daunting, which brings me to the last and perhaps most interesting mathematician for today. Meet Raymond Smullyan. He's the inventor of the printing machine we saw in the beginning, and the puzzle and everything. And that problem put Gödel first incompleteness theorem under a really clear light. He was an American mathematician, logician, philosopher, concert pianist, and professional stage magician. So after a rather unconventional academic journey, he became a doctoral student of Alonso Church. But his most wonderful gift to mathematics and logic is a vast collection of logic puzzles, stories, and challenges. They introduce all these abstract concepts in a fascinating, accessible, and fun way. I personally encountered Smullyan when I started studying computer science. And I have a theory of computability course. And I had an excellent, wonderful professor. He was called Mario Perez. He's a member of the European Academy of Science. And I was absolutely fascinated by those topics. So in the beginning of the course, we studied Cantor's diagonal argument. This is a proof about different, it was using a proof about different sides of infinity, to put it simply. Diagonalization, it was a very clever general technique to prove some things that actually Gödel used to prove his first incompleteness theorem. So I was fascinated by Cantor, so I was searching for books to learn more. And then I stumbled upon these books, Satan, Cantor, and Infinity, by Raymond Smullyan. And I loved it, like the stories, the puzzles, the clarity, like it was so great. So I continued searching and reading more books by Smullyan. He has books on chess puzzles that aren't your usual chess puzzles, riddles about island inhabitants that always tell the truth, he calls that the knights, or that always lie, the knaves, and all sorts of games. And all of them cleverly introduce very deep topics, such as recursive functions, automata theory, higher order logic, and the very limits of mathematics and computer science that we just talked about today. So after graduating, I started a PhD. And I got the chance to teach the very same course that so much influence had on me. So I recommended these books to my students to try and spark, the same excitement that I felt. Actually, I lent my copy of Satan, Cantor, and Infinity to one of them, and they never gave it back to me, so I couldn't actually use it to prepare this talk. So we are getting to the end. So if you take anything from this talk, I'd love for it to be, go find some Raymond Smullyan's books, dive into them, use your brain to wrestle with the puzzles and these abstract ideas. And I think using your own mind to unravel complexity is invaluable, and it's going to set you apart as a programmer or as an engineer. And above all, think twice before letting random students borrow your logic books. Thank you. Okay. So.